Hello, welcome to this webinar. I am going to talk today about the role of carbon dioxide removal, CDR, in IPCC pathways to limit global warming to Paris Agreement goals. My presentation is based solely on the assessment and findings of the Intergovernmental Panel on Climate Change, the IPCC, in the special report on global warming of 1.5 degrees Celsius of 2018. Although this topic has also been addressed in the contributions of working groups 1 and 3 to the fifth assessment report of the IPCC in 2013 and 2014, but not in the context of the Paris Agreement, which was agreed in 2015. As we know, one of the aims of the Paris Agreement is to hold the increase in the global average temperature to well below 2 degrees Celsius above pre-industrial levels, and pursuing efforts to limit the temperature increase to 1.5 degrees Celsius above pre-industrial levels, recognizing that this would significantly reduce the risks and impacts of climate change. So, in addition to addressing the impacts of global warming of 1.5 degrees Celsius above pre-industrial levels, the IPCC also assessed related global greenhouse gas emission pathways, which IPCC defined in the report as modeled trajectories of global anthropogenic emissions over the 21st century. In this slide, we can see a number of illustrative pathways limiting global warming to 1.5 degrees Celsius, but with different characteristics. While some of them maintain global warming to below 1.5 until the end of the century, others go a bit above, but below 1.6 degrees Celsius, while others go beyond 1.6 degrees Celsius. We refer to these as pathways with no, limited, or higher overshoot, respectively. And note that in all cases where a temporary temperature exceedance occurs, it is pushed back to 1.5 degrees Celsius by 2100. So carbon dioxide removal relates to a set of techniques for removing CO2 from the atmosphere that, in most cases, achieve net negative emissions to return to 1.5 degrees Celsius from an overshoot. CDR also serves to offset residual emissions, that is, those CO2 emissions that do not reach net zero by around 2050, which is a characteristic of all 1.5 degree consistent pathways assessed in this special report. So we see that CDR has an important role to play in both cases, and even more in the case of pathways with longer and higher overshoots. All the pathways assessed by the IPCC in the special report used CDR methods, but there are more publications focusing on two of them: afforestation and bioenergy with carbon capture and storage, referred to BECCS. If we look at the four illustrative pathways below the envelope of pathways assessed, we can see the emission reductions achieved through afforestation from the shaded brown color in the illustration on the left-hand side, which is characterized by rapid decarbonization, low population growth, among other assumptions. On the far right-hand side, the shadings in brown and yellow are associated with emission reductions from afforestation and BECCS in a higher overshoot pathway representing a resource and energy intensive scenario with high demand for transportation and livestock products, among also other assumptions. The 1.5 special report provides in Chapter 4 a description and an assessment of CDR options, where it can be seen that each one of them face different challenges to effectively contribute to the roles I already indicated, to offset residual CO2 emissions and to achieve the negative emissions necessary for the overshoot pathways, especially the higher ones. Although, as I mentioned previously, all the pathways assessed used CDR options, not all of them included BECCS. However, the overall set of pathways limiting global warming to 1.5 degrees Celsius with limited or no overshoot include this CDR option and indicate its potential contribution to CO2 removal from the atmosphere. As with all the options assessed, the ranges provided can vary significantly depending on assumptions made. For instance, for BECCS, some authors estimate its mitigation potential in 2050 as within the range from 1 to 85 billion tons of CO2, while others narrow this range down to 0.5 and 5 billion tons of CO2 per year, meaning that the mitigation potential from BECCS could not be sufficient for 1.5 consistent pathways. The difference in the estimates provided in the scientific literature often result, in this case, from sustainability concerns. For instance, assumptions about land scale, which could compete with food production, although per se, this might not be a good indicator, since high productivity agricultural land could provide the same potential in a smaller land area. But in summary, one could say that an effective BECCS implementation as a CDR measure depends on many factors, including the availability of coordinated policies and management to minimize the negative side effects and trade-offs, consideration of feedstock used, time frame, directed and indirect land use change emissions, among others. Another concern or constraint for BECCS relates to the availability of safe storage for the CO2. As I said, the BECCS is the bioenergy with carbon capture and storage. So this is storage might present a constraint for BECCS implementation. So another example of significant differences in the potential range indicated in the literature is for afforestation, estimated to be within 1 to 7 billion tons of CO2 per year in some publications, and narrowed down to 0.5 to 3.6 billion tons of CO2 per year when a number of constraints is considered. We know that biogenic storage is not permanent, or at least not as permanent as the emission reductions by geological storage. We also know that forest sinks saturate. We know that afforestation potentials are heterogeneously distributed, and that forest governance structures and monitoring capacities can be bottlenecks. So careful forest management is necessary to exercise the potential contribution of afforestation in 1.5 degrees Celsius consistent pathways. The direct air carbon dioxide capture and storage, referred to as DACS, another CDR option that captures CO2 from the ambient air through chemical processes and subsequently stores it in geological formation, faces as one of its main challenges the availability of safe and accessible geological storage. In addition, the estimated cost of DACS differ significantly in the literature, ranging from $20 to $1,000 per ton of CO2 in some publications, and from $100 to $200 per ton of CO2 in others. As with these three examples, all the other options have their own bottlenecks, and their potential risks and costs need to be further evaluated through enhanced research. We discussed the issue of the scale of CDR that might be necessary. And the special report indicates that there are still scientific uncertainties related to the implementation of large-scale CDR. The report notes that ambitious system transitions in all sectors, behavior change, and demand-side management can significantly reduce emissions and substantially limit the reliance on CDR to limit warming to 1.5 degrees Celsius. However, it recognizes that unless affordable and environmentally and socially accepted, CDR becomes feasible and available at a scale well before 2050, 1.5 degrees Celsius consistent pathways will be difficult to realize, especially in overshoot scenarios. So I hope that this presentation stimulates all to consult the 1.5 special report and the assessment reports from the IPCC. And I also note that additional scientific findings on this issue will be available in the next assessment report of the IPCC in 2022, based on more updated scientific literature. Thank you very much.